So I'm Kurt Hillegas from Princeton University. I'm the Director of Research Computing there. We have 5 major computational resources totaling about 17,000 cores and about 550 teraflops of computational power. I have a group of about 10 people who work with me to help make things run. And we've been doing this for a little bit over 10 years. We started in 2002. We're a little bit interesting or strange because our group, rather than being an IT group or an academic institute or department group, we're a mixture of everything. So I have reporting to me people from OIT, people from PIXI, which is our Institute for Computational Science and Engineering. I have people from astrophysics reporting to me, partial people from other areas. So we really do have a collaborative central research computing system. I'm going to talk a little bit about our job scheduling models and challenges. I mean, you'll see the slide that actually has challenges on. I say opportunities and challenges. Hopefully these opportunities will be grasped by the people writing codes to help with scheduling so that we can make those challenges into opportunities. So the way we do things at Princeton is a little bit different. It's actually become known as the Princeton Model among some people out there. And so when we buy our systems, the central administration doesn't decide we're going to buy these systems, and of course the researchers are going to use it because we bought it for them. And the researchers don't go off independently and buy their own thing. We used to do that in the past. I know that we used to have a researcher who got a data feed once a week. That data feed took its cluster about 2 days to run, and then the cluster sat there idle for 5 days. So we have brought everyone together to try to get as much leverage out of their shared resources so everyone can get at least as much as they pay for. We do have some departments like genomics and neurosciences that have very expensive instruments. And so the time slice that it takes to do the measurements on those instruments, to take a gene sequence, is so expensive that they want to make sure that the direct processing that has to happen during that gene sequencing or during the measurement of a functional MRI happens right next door so that someone with a backhoe doesn't cut the cable or so that there's not some network congestion that gets in the way. So they have their own resources. But many, many of the departments have now fully bought into the central shared environment for HPC. Anyone in the university can get an account on any of our systems. All they have to do, they have to have a faculty sponsor or a full-time employee, research staff, someone who's definitely full-time at the university. A student can't sponsor himself or herself for an account. What happens is the first person from the faculty members group who wants an account writes a short proposal, 2 pages maybe, a couple of references, basic scientific background. The most important thing to us is a description of what their computational resource needs are going to be, just so that we understand the impact of what they're doing. We don't tend to turn those proposals down. Every once in a while, recently we had one, a researcher wrote one that was very kind of non-specific, and it wasn't clear what the researcher was going to do. We sent the proposal back and said, look, think a little bit harder and let us understand what you're trying to do. So not only do we know that we're getting scientific impact out of what we're doing, but we know exactly how many resources you're planning to use. But in general, these things tend to get accepted. It's a good exercise for graduate students to go through, and it lets us know who our customer base is. 20% of our systems, or the target is 20% of our systems, are centrally funded. So the central administration, either through our Institute for Computational Science and Engineering, through OIT, or directly from the Provost's office, will pay for at least 20% of the system. And what we find is the way we do our scheduling, if that percentage goes down below 20%, everybody starts getting phone calls, including the Provost's office, which is a very good inspiration for the Provost's office to up the ante. Our most recent cluster is a very big cluster. It's 10,000 cores. It has 200 GPUs and 8 Intel Xeon Phis in it. That cluster is paid more than 50% by the central administration directly from the Provost's office because it was replacing 2 very large clusters. Didn't have funding sources, and the provost saw the need to make it sustainable so we could continue going on. The rest of the funding for our clusters comes from faculty, departments. There are grants, we've written grants, so for example, our storage system is from an NSF MRI grant. I'm the PI on that grant. So that's kind of like centrally funded, but it's funded through a grant organization. So we gather together all of this funding, and here's where we come to the big difference between the way Princeton does things and a lot of other institutions do things. The idea of a condo doesn't quite work. It's maybe more like a timeshare. It's what we like to think about is that it's not like everyone's buying a part of a condo and you get the bathroom, so you have to sleep in the bathroom, and you get you don't own your specific nodes. There aren't nodes sitting there waiting for you to run on the nodes in time. We don't guarantee, but we say we are going to try to make sure that if you're submitting a job that's going to run for less than a day, you're not going to wait more than 4 hours to get that job to run. And if you're submitting a job that's going to take an hour, we're hoping that in 10 minutes it's going to start up and you'll be able to get that running through. So we try to scale the start time by how long your job is and how wide your job is. If you're asking for half of a cluster, it's going to take you a lot longer to get your job scheduled than if you're asking for 32 cores or something like that. And then with that comes the promise that over a time period, and for different clusters it's different, most of them it's over a 2-week time period, or our newest cluster it's over a month. You're guaranteed that if people from your group are trying to use that system, if you actively have jobs sitting in the queue for that month, you're guaranteed that you're going to get at least the proportion of the system that you paid for. So if you paid for the equivalent of 10 nodes on the cluster, you're going to get 10 nodes times 30 days worth of utilization during that particular month. And it works out very well. We have faculty who are very happy with the way this is working, and it helps to create a lot of community among people, because what happens if someone starts misbehaving, first of all, we usually notice, we turn the knobs and smack the backs of wrists. But it's a social community, and someone sees someone else taking up what they view as their time. They're not shy about writing an email to that person and saying, you really shouldn't be using that much time. You're going beyond what you've contributed. But what we find is almost everybody who's using the systems, who's actually trying to use the systems, gets more than they paid for. Sometimes significantly more. And what's even better is if someone has a conference coming up, or if they've got a paper review that they've got to respond to quickly, we've got a community that we can go out to and say, look, we've got to allocate a part of the system so that this person can get their job done in a certain period of time. People are happy to get out of the way because they know that'll happen for them if they do it in the future. So that's how the Princeton model works. And we do have a number of challenges that we have to deal with in this model. And here's where we get to test technology. So I'm going to see if I can actually click on this. Oh, it looks like it's going to start. Here we go. So we've got a movie. This is what we call a shake movie. Jerome Trump is the PI for this project. This is a website that they collect the seismic data from all the sensors around the world, and in near real time, they calculate the seismic wave propagation around the world, and you'll see it's going to look very boring for a while. This is actually a 7.8 earthquake that happened down between the tip of South America and Antarctica on Sunday morning in the wee hours of the morning. It was 9 o'clock UTC, so that was probably about 3 o'clock in the morning it happened. And we'll sit and wait, and what you'll see is as this propagates back around, you're going to see it refocus back in near the same spot that it started. If the world were perfectly spherical and all had the same consistency, it would actually come back and focus to that same spot, but it doesn't quite focus to the same spot. But so we need to be able to schedule these jobs. We need to reserve time that these need to go out in near real time, because the media uses these. There are scientists around the world who depend on the synthetic seismograms. The movies are great. The media loves the movies. But the real thing, the real science that's happening is the synthetic seismograms that they're calculating. That scientists can then go out and use that information to adjust the models that we have for the Earth, so they can improve the models and we can better predict how earthquakes are going to propagate. And has it come back around yet? It still has not come back around. You can see we're starting to get some little stuff here and there. You'll start to see the waves coming back in. So scheduling this is one of our big challenges. The first attempt that we made at scheduling this failed miserably. And it failed miserably on a social front. The first cluster that we were running this on, everyone decided that they wanted to own their own. They wanted to have a queue for Dr. X and a queue for Dr. Y and a queue for Dr. Z's group. And what we found is Dr. Z's group would go to a conference and there was nothing being used over here, but because we had chunked things up into little pieces, it was going idle. There was someone over here in Dr. X's group who wanted to run jobs, and they couldn't run the jobs over here because this is sitting idle. Since that time, we've been able to get past that, and we're able to schedule things a little bit better. I think the movie has finished. Hopefully we saw it come back around. So what is the success that we've had using Moab? We've got a scheduling mechanism that involves a number of things. We've been using Torque and Maui for many years. About 3 years ago, we bought Moab. When we bought Moab, we went from a utilization on our clusters that was running just above 80%. I had told our third scheduling mechanism, his name's Bill Wixer. He's absolutely wonderful. He goes in, adjusts the knobs, and makes sure that all the researchers are very happy. But he was driving things. I said, let's try to make 80% all the time on all of our clusters. And he was driving us just above 80%. When we installed Moab, doing pretty much the same amount of work, maybe even a little bit less work, we're now driving at least 2 of our clusters above 90%. Actually 3 of them. The ones that aren't above 90%, the major contributors to those systems don't want them driven that hard. They want to have some stuff free so that if they need to start stuff up right away, they can do it. So Moab has given us a significant advantage over Maui. It does a better job of filling in the little holes. I like this thing over here. I thought I was going to have to compete with it, but I have something to clean at here. The researchers are happy. We do get complaints. We have a researcher right now who wants to do 30 million CPU hours worth of work in the next year. Our biggest cluster has 80 million CPU hours in it. His advisor has contributed about 3% of that cluster. He's never going to get 30%, more than 30% of the cluster. He has actually gotten over 10% of that cluster during some time periods and he's been trying to work. But so not everyone's happy, but a lot of them are. We report regularly, and we report out to the faculty on a quarterly basis how much each faculty member's been using, how much each researcher within a faculty member's group has been using. People can look online. We use all of the Moab and Torque utilities. We make them available to the researchers so that they think, you know, my jobs are queuing too much. Why are they queuing too much? They have the utilities that they can run, and they can say, oh, I'm not getting priority right now because my advisor paid for 3% of the system and I used 14% of the system over the past 2 weeks. So my priority is going to be a little bit lower than I expected to be. Scheduling this way has helped us to build a stronger community. It's made it, we don't have draconian rules that are, you know, you get your allocation sheet in a month and you run out, and you know, we haven't built boxes in which people have to fit. It's a very social environment where people use what they need, they cooperate with each other, and it's helped to build, on the scientific side, the community among the researchers in different disciplines. And finally, it has helped us to minimize the gaming of the systems, because what we find is the more rules we build in, the more people try to find ways to work around the rules. And what we decided is, we see someone trying to game the system, we call them on it. We say, look, there's no reason to do what you're doing this way. Tell us what you need, we'll help to work with you. And no, you're not going to get a third of the cluster if you haven't paid for a third of the cluster, but we'll help you to get your work done. And so we've made our jobs easier by doing a thing in ways that are easier or more palatable to the faculty. So we do have a little bit of a different scheduling challenge, and this one comes into that segregation piece, the thing that we don't want to do. I mentioned that we do have a set of researchers that don't want their cluster fully scheduled to 100%. And part of the reason for that is the way they have found that their jobs work the best is totally antithetical to the way, Cray has us scheduling things over here. They don't want to have everything packed onto as few nodes as possible. They actually want everything one task on each node. They spread their jobs out. They're running on a cluster of 308 nodes, and sometimes they run 308 task jobs that run across all 308 nodes. And we'll have 12 of those jobs running on the cluster at the same time, and one of them fails and crashes everything. And we have no idea how to troubleshoot that whatsoever. So it's a challenge. It's a technical challenge beyond scheduling, but this is one of the things that we have had to deal with. And we would actually like to have fewer, larger resources rather than chunked up resources, because we don't want to waste that time. We want to have 100% utilization. So I'll play this movie. This is from Franz Pretorius in physics. This shows binary neutron stars merging from a dynamical capture event. So what that means, you're in a dense star cluster, and two neutron stars get close enough together, and this happens very, very rarely. They pass close enough together that they get captured into a kind of little dance with each other, and eventually you'll see they come together and they combine into a single bigger neutron star. You can see that they look like they're spinning. That spinning is actually a mode in the neutron stars that is affected by the gravitational pull of the other one. So it's almost like tidal type stuff going on. The movie has stopped. The movie stops right there because it gets very complicated after this, and they haven't actually propagated the calculation. In about 100 milliseconds to a few seconds, that neutron star implodes on itself and becomes a black hole. And so that goes beyond the model that they've developed. The mass of this star is about 1.4 times the mass of the sun, and the individual neutron stars that were rotating around each other were about 12 kilometers across. So they were very dense. So let's talk a little bit about the challenges and opportunities. What do we want? What do our researchers want? The first thing that we have to really stress is scheduling is fundamental to the operation of high-performance computing systems. If the scheduler is down, no one's jobs are running. We're wasting very precious resources every time the scheduler is down. Every time people have trouble getting their jobs to run, every time that jobs are inadvertently killed, we are losing money on the resources that we paid for. Not just the capital costs, but we're still running the electricity to run them. The electricity is about 50 to 70% of the lifetime cost of an HPC resource. So one thing that we struggle with all the time is software upgrades and stability. We need to make sure that those scheduler upgrades can slide in. They can slide in easily. We would like to not have to take things out of production in order to do that. We do have users for which every time we restart the scheduler, their jobs, they have very complicated job scheduling stuff that has interdependencies between jobs. They have to go back and start over from scratch and resubmit everything. We don't want our researchers to do that. We also don't want things to crash, and we don't want jobs going wild. We don't want things. So this is a big concern of ours, and something that we continue to push on to make sure that this is as stable as we can possibly make it. We do have different architecture requirements. So we have these people who need to spread their jobs out. We have people who need them packed close together. We have people who need 8 gigabytes per core, and we have other people who need 4 gigabytes per core. So our clusters actually do have different sections. So one of our clusters is half 8 gigabytes per core and half 4 gigabytes per core. But now we've drawn those little boxes again, and we don't want to divide the clusters up into smaller clusters. We want to be able to schedule this broadly, so we have to figure out how to deal with that. Accelerators are a huge challenge right now. Scheduling on accelerators is very new, and getting it to work right and smoothly, and getting to be able to do the accounting so we understand, so that we know when a person says, I'm allocating 1 GPU. So in the end, when that comes back, we know that they used 1 GPU and they used it the whole time. The last thing that we want is someone to schedule a job, say that they need all the GPUs on the node, and really all they want is the 16 cores that are riding underneath of that, and they just said that they thought they could game the system to get underneath and use those cores. One thing that we really would like to be able to do is give people multiple allocations. So the way we do the allocations is based on the PI's contributions to the system. But, for example, let's say we have someone in our chemical and biological engineering department who's contributed 3% of the system. But maybe the chemical and biological engineering department, independent of this researcher's contribution, contributed a little bit more. And maybe our School of Engineering and Applied Sciences, of which they're all members, applied a little bit more. Well, a researcher in this guy's group, we can only choose one of the three right now. We can't say, okay, they can be part of all three of these allocations, they just have to choose one. We'd like to be able to do that a little bit more fairly so that everyone's getting all the benefits of all the contributions that they should be a part of. Cross-cluster scheduling is something that the schedulers are ready to do. Everything's there, ready to do for us. We just need to get our researchers ready to do it, and we have to work on their cultural and social, make sure that they understand that they have to, they can't just submit a job that they normally would, and we have different architectures. They have to make sure that they have a way to figure out what the architecture is and run the right executable for that architecture. The next slide that I'm going to show has to do with disk scheduling. We have people who would like to schedule very large scratch disks for a period of time, and so large that it's not a normal part of the scratch that we would provide for the system. And finally, license scheduling. How do we make sure that people are getting fair usage of the floating licenses that the university has contributed to? So let's talk a little bit about some work from Neuroscience. Jonathan Cohen is the PI on this. Kai Lee and Nick Turk-Brown are working. Kai Lee. Jonathan Cohen is the co-chair of our Neurosciences Institute. Kai Lee is a professor in computer science, and Nick Turk-Brown is a graduate student working with them. So these pair of images may look like a standard fMRI image that you may have seen in the past. This is a brain, obviously. But these lit up areas aren't the areas of the brain that are active. These lit up areas are the areas of the brain that are active in a correlated way. Right? And that's correlated not necessarily at the same moment, that's correlated over time as a response to an individual stimulus. So on the far side, we've got an image that shows the little black piece up here. I don't know if this is a pointer or not. The little black piece up here shows the frontal part, and then the big arc around the other side shows the rear portion. And the lines going in between show the correlations between the two pieces of the brain. And they may or may not be at the same time. One might be, milliseconds later than the initial response was. What's interesting is the blue lines are a response to looking at a face, an image of a face. The red lines are the response at looking at an image of a kind of generic scene. You can see, qualitatively, you can see something very different between the blue lines and the red lines. There's obviously some circuitry built into our brains from the get-go that does a lot more of this correlation when it's looking at a face than it does when it's looking at a standard scene. So what they would like to do is they'd like to be able to take an entire fMRI, all the voxels of the brain, over all of time, and do the complete correlation of that. If they do that, they're talking about somewhere between 10 petabytes and 100 petabytes worth of data that they're going to have with the current resolution of MRI. They want a scratch file system that they can have just during the time that they're doing this. So we would need to be able to schedule that file system. First, we need to find funding to buy a 100 petabyte file system. But with that, I think I'm going to ask if anyone has any questions, and thank you for staying through my talk. Size of our user base, we in the past year we've had 440 active researchers. They come from 84 sponsoring faculty and a total of 21 academic departments. size of the typical job, we have jobs ranging from 1 core through hundreds, if not 1,000 and more cores. And we have jobs that run from 5 minutes up through, the longest jobs that we standardly will allow is 5 days. We do have some major contributors who have jobs that need to run for much longer. They're using commercial codes. They aren't checkpointable. And so we do allow up to 30 days. We do maintenance once a month on all of our clusters. We actually do it all on the same day now. So people are limited to that kind of 30 days. There again, it's a very social environment. So if someone needed longer than 30 days, we would have the possibility of negotiating to skip or delay 1 month's maintenance window. Those really long jobs tend to be single core or very few core jobs. Do we use preemption? That's actually, thank you for saying that, because I wanted to talk about that. We have used preemption. Remember when I said we had trouble with this cluster that got kind of chunked up into different pieces? People who hadn't contributed to that cluster got put into what was called the risk queue. And the risk queue had preemption. And the problem there is that they were getting preempted all the time. And not all of them were doing checkpointing, and it was really wasting a huge amount of resources on the cluster. We managed to convince everybody that that's not the right way to do things, but we're now talking about using preemption from a totally different perspective. We'd like to start doing some scavenger type scheduling. We have some very sophisticated users who, if they can get 10 to 15 minutes of CPU time on a node, they can effectively use that checkpoint and have made progress. So we can stop talking about settling for 90% utilization, and we can talk about nearly 100% utilization if we allow those people to go in. And they would be preemptible, they would be sophisticated enough to know. It wouldn't be a default that they would be put to, but they would have to know to say, I want to do this. I know what I'm doing and I want to do this. Any other questions? Go ahead. Yes. Right, so all of our clusters have a test queue, and that test queue is 1 hour long. The test queue is the only queue that has access to all of the nodes in the cluster. The other queues, the longer the job runs, the less proportion of the cluster that queue has access to. So we try to make sure that if you're doing development and you need to run a job for a short period of time, that you can get that job in really quickly. And that we're hoping that 10 minutes is all you're going to have to wait for a test job. And we do discourage people from doing production in the test queue. We have had that happen as well. Any other questions? Excuse me? How long is what? Queue? 7 days. 7 days, and that's a very special. That's less than half of the cluster. It's a very special queue. We strongly discourage people from using that, because the bigger anything is, it's harder to fit them into a puzzle. It's a multi-dimensional puzzle. Yes. No, they have to specify the wall time in the job. We actually set a default wall time of 10 minutes. So their job will die if they don't. Yes. Other questions? Great. Well, thank you very much for coming to the talk.